Hello, multi-level modeling class. This is Zachary Roman, and we are back for another lecture. This week, we will be talking about piecewise or growth modeling. So in the last few sections, we covered longitudinal modeling, and we looked at linear trends and group differences. And this time, we will be looking at a different approach to modeling longitudinal change. This is called piecewise modeling. So let's get started. So we'll start with the concept of longitudinal interventions. We'll look at piecewise models and the model formula. I'll discuss developing the slope representations. I will show you an example interpreting these models. And then I will do all of this again with a between level grouping variable. So let's talk about this. Some experimental designs will track participants for multiple time points on some DV. And then at some point, an intervention will occur. And multiple time points are measured again after this intervention. So for example, we could measure depression for 3 time points, begin a therapy, and then measure again for 3 time points after it. In another context, this framework is useful for naturalistic experiments, sometimes called quasi-experimental designs if done on purpose. And this can be thought of as having an intervention in time. So let's say we're measuring toxins in different locations in the ocean at multiple time points, and an oil spill occurs, and then we measure at multiple time points after this event. So the idea is that we are looking at more than just pre-post, but multiple pre and multiple post measures. So this can be really good for things such as like weight loss. We measure people's weight over time to get an idea of what their general weight gain or loss trajectory is. And then maybe we do some type of intervention with all of them, like introduce them to a spinning class or teach them to rock climb or exercise or change their diet. And then we measure for a period of time after that to get an idea what the change in the developmental trajectory of weight would be. So here's how this data may look. We have some measurements at time point 0, 1, and 2, and then something occurs at the dotted line, and we measure the change in the trajectory. Now, this could be approximated with a curvilinear slope, but we could also measure it with multiple linear slopes. And here's an example of this. Red being pre-intervention and blue being post-intervention. The shaded outlines are each individual's trajectory. They're partially transparent, so where we have a lot of people overlapping is a darker color. But notice how in the last plot, we could use a curvilinear effect to measure this trajectory. Here we could use just linear trajectories, one prior to an intervention and one after. Now I will only be showing a single or 2-slope piecewise growth model today. But we could have many. We could measure something and then an intervention occurs and we look at the trajectory change, and then another intervention occurs and we could look at the trajectory change. In that example, maybe we have weight loss again and we're just measuring people's weight trajectories over multiple months. Then we give them a weight loss intervention. They go to a CrossFit class and we measure them for another set of like 6 months. And then maybe the CrossFit class ends and we see if any of the weight loss that they obtained maintains, or if they start to gain weight again because of the completion of the class. So we can have multiple pieces here approximated with linear trajectories. So the model formulation is not much different from what we've been working with. Here we have a situation where we have a random intercept, a random slope of the first slope, and a random slope of the second slope. And so in this formulation here, I have TI T1 And this would be a time variable, which is dummy coded for the first time points. And then TIT2 is the time variable for the second set of time measurements. So in that formula, TIT1 would encompass these time points, and TIT2 would encompass the latter time points, the blue time points. So that's all. And in this formula, I'm including a random intercept and a random slope for each of the slope estimates we will have. So notice here that we will have one intercept and two slope estimates. So tying this back to the plot, our intercept be the expected value here when time is equal to 0. The first slope will be the slope of the red section here, and the second slope will be the slope of the blue section. All right. So the biggest obstacle to using this method is really just coding for it. And I'll show you how to do this in R, as our R session is integrated with these slides today. So this will be the only video for this week's lecture. So in this example, it's the same as the plot. The intervention occurs between time 2 and time 3. Time, the vector here, time in this example table, is the initial measurement occasions, right? So time 0 is the first measurement or baseline. Then we have 1, 2, 3, 4, 5. So we have 6 measurements of time. These are all measurements for person 1. I then show person 2 as well. And the data frame continues. What we need to do is use dummy coding, similar to categorical effects in regression. We need to use dummy coding to balance the time points so that they reflect these different slopes. And what we need to do is balance it so these slopes overlap at some middle time point. And so the first slope being the first the first 3 time points here, is reflected by -2 for time point 0, -1 for time point 1, and 0 for time point 2. Notice that time 2 is 0 for all of those effects. Time 2 then will be coded as 1 for time point 3, 2 for time point 4, and 3 for time point 5. This is what our matrix looks like. Again, the key part is no matter how many measurement occasions we have, if we have 30, they will overlap right in the middle at 15. At 0 for the second vector and 0 for the first vector. They then will count away from each other and balance. So in the 30 sense, time 1 would go from -15 to 0, and time 2 would go from 0 to 15. Now this coding scheme goes all the way across the data set, right? So for the second person, it's the same thing. Third, all the way through n. Now this is how I accomplish this in R. I use an if-else statement. So pretty much what I'm saying is the time vector here is this original vector of time. And I'm saying if the time is equal to 0, yes, give me a 2. Otherwise, if time is equal to 1, give me a -1. If time is equal to 2, give me a 0. Everything else is a 0. That's what this last argument says. Give everything else a 0. And that's how I produce the time 1 vector. Now for time 2, I say if the time variable is equal to 2, then make it a 0. If the time vector is equal to 3, then give me a 1. If the time vector is equal to 4, give me a 2. If the time vector is equal to 5, give me a 3, everything else 0. And that's how we get this vector here. This might be new for some of you, if-else logic. It is a core principle in computing, and I'm always here to help you understand and do these things. But this will work for our example that we will be working with. Okay, so the syntax for the growth model in R is quite straightforward. Again, the most complicated elements are deriving that dummy-coded matrix of time 1 and 2. So my snake was dropped here, but it is score tilde or snake is predicted by a fixed intercept plus time 1 plus time 2 plus the random effects, which I include as a random intercept, a random slope of time 1, and a random slope of time 2. And let's take a look at what our results look like. Okay, so let's take a look at the plot. This is what I will be tying the interpretation of these results back to. Remember, time 0 is this middle time point here. So this is where we'll be starting with the intercept and how it's reflected in the model results. So let's start. The intercept is 10.01. Okay, what's that saying? Well, when all of the predictors are 0, and since our predictors are just time, when time is 0, the expected value of score, our dependent variable, is 10. Here we are. That is the fixed intercept, so that's our average intercept across all people. Now the random intercept is 4.2. So that is the variance of the fixed intercept. What's that telling me? Well, we have variation equal to a variance score of about 4. So if we square root that and use the standard deviation, our knowledge of normal distributions tell us that some proportion of people, right? So 64% fall within plus or minus 1 standard deviation. 64% of the participants are between about 8 and 12, and then 98% within 14 and 6. So these individual trajectories show us that. We have some variance right here around our intercept, and that is the random effect. Okay, so we have a fixed slope of time 1, and it is a very small estimate. It is 0.03. That is telling us for a 1 unit increase in time, so from this measurement occasion to the next, the expected increase in score is about 0. This slope is effectively 0. So the model is telling us that there is no growth in slope 1 of time 1, which is this initial pre-intervention trajectory. And the variance, or the random slope for time 1, is 1.03. So this is telling us that there is some variation in the individual trajectories here, but not much. So some people are seeing slight increases and slight decreases, but not by much. Okay, now time 2. This is where things are interesting. The fixed effect of time 2, or the fixed slope, is negative 2.0. This is telling us that for a 1 unit increase in time in the blue section, so from 0 to 1 or 1 to 2 or 2 to 3, we are expected to see the score go down by 2 units. So from here to here, we see a 2 unit decrease here. 2 units. Okay, so that is our fixed slope. Now there is a lot of variability there. This time to random slope is telling us that the standard deviation is about 1.44. So some people are seeing more and less growth. And we can see that in these blue lines here, that some people are declining faster, some people are declining higher. Okay. So that is the general concept and formulation of a piecewise growth model. Now, doing last week's homework, we talk about I have you guys think in the bonus question about interventions and making an experimental argument about if some intervention works. This experimental design makes sense. We test people before and then after an intervention. But it's also useful to test another group and maybe not expose them to the intervention as well. Okay, so now in the between and within effect situation, we have a situation where we have exactly what we just covered, where a group is measured at multiple time points, then an intervention occurs, and then they're measured at multiple time points again. In the oil spill example, this could be we're sampling one region for toxins in the ocean, we measure for 6 months. An oil spill occurs, we measure for another 6 months. But now we also have a between group condition, where one group experiences the intervention and the other does not. So in this situation, we have maybe a region of the ocean we're measuring which does not have an oil spill to provide as a control condition for comparison. In an experimental context, this could be one group of people does not receive therapy and they're measured over 12 months, and one group is measured, for 6 months, then therapy begins and they're measured for 6 months during therapy. Now, this example scales really well, or this method does, because we can have more than 2 groups here. We can have many groups. So we could have a control group, a 10 milligram caffeine group, 30 milligram, etc. So we're not constrained here to a number of groups. Here's what this situation would look like with our running example, where we now have a control condition which does not experience the dotted line. They are not exposed to the intervention. And an experimental condition which is. So we have measurements for both of them prior to the intervention for the experimental group, and then we have these piecewise slopes. Now, the only big difference here is that we are including condition as a main effect. So for our model formula here in R, we have the DV score predicted by time 1, the initial slope, time 2, the post-intervention slope, the condition variable, which is either a control or experimental group. It's just a dichotomous 0, 1. Then we have an interaction between the condition group and the first slope, and the condition group and the second slope. We then have, in this formulation, I just have the random intercept and random slopes of time. Now, we could also include random slopes of the interaction terms, and I'll talk a little bit about what that would mean. Okay, so here's our model results. Let's break these down. Starting with the intercept. Because the control condition is coded as 0, the intercept is telling us the expected value at time 0 for the control condition on the DV here. So this is the expected value for the control condition because it is coded as 0. Notice here that it says condition EXP. This is the comparison group, okay? So time 1, this is the slope for the group coded 0 at the pre-intervention stage. This is the slope. Time 2 is the slope for the group coded as 0, the control group. And the second, after the intervention, right? Now, condition EXP, this is simply just the mean difference at time 0 of the experimental condition and the control condition. So the experimental condition is just a little bit lower than 10.06 at time 0. The time 1 by condition EXP interaction here tells us if the slopes are different between the experiment and the control group prior to the intervention. So this 0.10 is telling us that the experimental conditions slope of the initial time phase is a little bit higher than the slope of the control condition. which is what we see here. So looking back at the plot, yes, we see the experimental condition had a slightly higher slope, not by much. It's increasing. What's really interesting to us is that the interaction of the experimental condition in time 2, this is telling us we have a significant difference in the slopes at time 2 for the experimental condition. So the experimental condition is about, well, round up to 2. Has a slope of about 2 lower. Because we're measuring decline here, it's lower. But we see that the experimental group here sees a much greater decline. And that is what we're learning right here. Now, this is all just regression interpretations, and you should probably be familiar with these. The only extension here is this additional slope. Now, the random effects provide us with some information here. The intercept is telling us the variance around the intercept regarding the control conditions expected means. Time 1 is giving us the variance around the slope. We don't see much in the control condition at time 1. In the second arm of the experiment, time 2 here though, we do see a relative deviation here in that some of the slopes vary. I did not include the time by condition interactions in the random effects, but we could do that as well. And this would simply tell us how much variation is there in the difference of the slope between these two groups. Do some people have a much bigger difference and some people have less? This is very testable as well, although I do not include them here because the model is already relatively highly parameterized. Now here we could also inspect the correlations of the random effects. For example, time 1 in the intercept, this is telling us the higher the person's intercept, the lower their slope at time 1. Here we're seeing that the higher the intercept, the higher their slope in the second arm of the experiment. Or here we're seeing that the higher their time 1 slope is, the higher the time 2 slope is. All right, guys, so that is the general idea of the piecewise models. I'm not going to extend this any further, and this is going to be it for this week. But the general idea is you have some flexibility in these events occurring across time. And you shouldn't be constrained to simply thinking pre-post when we can get more information looking at developmental trajectories before and then after some type of effect. These models can really scale up and we can really get some informative results regarding these things. So take this information and go forth and develop really exciting experimental designs, which provide us with, good evidence for change. So thank you very much for joining me for this week's lecture. Again, there's no independent R lecture, and have a great week. Thank you.